Okay, let's dive into this. We all kind of learn this basic idea in physics class. These tiny, unstable particles, they don't stick around forever. They decay. 1 second they're there, and the next, poof, they're gone, replaced by something totally new. It seems pretty straightforward, right? A basic rule of the universe. But what if that poof, that whole vanishing act, isn't what's really happening at all?
I mean, it sounds like a simple question, doesn't it? When a particle decays, does it just blink out of existence? Our gut feeling says that can't be right, that things don't just vanish. And you know what? It turns out some physicists are asking that exact same question.
So before we get into the really wild new idea, we've got to have a solid handle on the classic one. This is the standard view, the absolute cornerstone of particle physics that has worked incredibly well for decades. Right. So the big thing to get here in the standard model is that decay is an event. It's instantaneous. One moment you have a neutron, the next, bam, it's gone. And in its place, you find a proton, an electron, and an antineutrino. It's not a slow fade out. It is literally like flipping a light switch. This whole view is about playing the odds. We can never say when one specific particle is going to decay, just that there's a 50-50 chance it'll happen within a certain time frame. That's its half-life. But the decay itself, whenever it finally happens, is treated as happening in an instant. But what if that's not the whole story? What if instantaneous is just a side effect of how we're measuring the world? And that question, well, it leads us to a really fascinating alternative. And this is the core of the challenge. What if the particle doesn't vanish at all? What if instead it's going through a change so deep that our tools, which are basically built to see things as on or off, just can't register it as the thing it used to be? Maybe the problem isn't with the particle, but with our perspective. This quote just nails it. It completely reframes decay. A particle doesn't just stop existing. Instead, a little piece of reality itself, the very fabric of the universe, is smoothly and continuously shifting from one state to another. So here's how this idea gets built. First, you just have to reject the idea that anything happens instantly. Second, you swap out the idea of annihilation with transformation. The particle's properties literally morph and blend into a new state. And third, you realize our measurement tools create this illusion of a sudden switch because they can only see particle or not particle. They're totally blind to that smooth transition happening in between. Now, what's really cool about this slide is how clearly it just lays out these two completely different worldviews. Check out the particle fate row. In the standard view, it ceases to exist. Poof. But in this new view, its properties just blend into something else, something new and unobserved. That is a huge difference. One is a dead end, the other is a continuous journey. Okay, to really get on board with this new idea, you have to take one more giant conceptual leap. You have to totally rethink what a particle even is in the first place. So in this way of thinking, particles aren't these little separate billiard balls flying around in the empty vacuum of space. Nope. Instead, reality itself is one single, unified thing, like a fabric. And a particle, it's just a temporary, localized ripple or vibration in that fabric. It was never really a separate thing to begin with. And this is the perfect analogy. Think about it. You can see a wave, right? You can measure it, track it, but that wave isn't a separate thing from the ocean. It is the ocean, just in a particular temporary shape. This new idea suggests a particle is just like that, a temporary shape on the fabric of reality. Now, it's really, really important to get this. This new perspective isn't being sold as the final answer. In science, sometimes the most powerful ideas aren't the ones that give us all the answers, but the ones that open up a whole new world of questions to ask. And that's what makes science so exciting, isn't it? A truly great idea doesn't just solve a puzzle. It reveals this huge new landscape of mysteries to go and investigate. It just makes the universe bigger and way more interesting. So, here's the first big puzzle. If this is all a smooth, continuous transformation, why are the end results always so neat and predictable? When a neutron decays, we don't get some fuzzy in-between blob. We get a perfect proton, a perfect electron, and a perfect antineutrino every single time. How does a smooth process produce such specific, discrete results? And that, of course, leads to the next massive question. Are we just stuck seeing on or off forever? Or could we, maybe one day, build something sensitive enough to actually catch a glimpse of that in-between state, to actually witness the transformation as it's happening? And then you've got the biggest hurdle of them all, quantum mechanics itself. Quantum physics is famously weird, all based on probabilities and uncertainty. A particle can be in many states at once until you look at it. So how does a smooth, continuous, gradual process fit into that bizarre world? That's a major, major puzzle to solve.
So in the end, we're left with this really powerful idea. This hypothesis suggests that one of the most fundamental things we think we know might just be an illusion, a trick played on us by the limits of our own perception. And that forces us to ask the ultimate question. If we could be that wrong about something this basic, what else are we missing? What other incredible truths about our reality are hiding just beyond the edge of what we can see?